Welcome to another physical sciences lesson. We're going to be revising the topic of electromagnetism today. So come along with me and let's have a look at what we're going to be doing. So if you remember, electromagnetism deals with an important idea. It deals with the idea of the relationship between electric current and magnetism. And in the first instance, we recognize that when you have an electric current, whether it be in a straight conductor or a loop or even a coil, what we'll recognize, it can produce a magnetic field. And so that's the first relationship that we're going to look at. But there is another relationship. And the other relationship is to say, if we have a magnetic field, can we produce some sort of electric current? That's known as electromagnetic induction. We'll have a look at that a little later. But let's start by looking at the first type of relationship, the relationship that is related to the starting point. We have an electric current that produces a magnetic field. And we can see this happening all around us. In fact, that's the question I'd like you to think about. What difference does electromagnetism make to your life? Now, you see, science isn't something that's just found in textbooks. It's something that we come across every day. But it's important for us to recognize as we see things around us, that's the principle of current electricity, or that's the principle of the heating effect, or that's the magnetic principle. So look out for those. What difference does electromagnetism make to you? Well, think about it. Be on the lookout for it, and as we explore further and as we revise this section, let's have a look at it. So I want to remind you about this idea of a magnetic field. A magnetic field is just a region in space. And it's like a gravitational field or an electrostatic field. But the only thing is that when we have objects that have magnetic properties. So objects with magnetic properties, and there are not many of them, when they're placed into this region of space, they will experience a force. And that's what a magnetic field is. It has a certain shape, a certain pattern. It's strong in some places, it's weak in other places, and we recognize it's really important. In fact, around the Earth, there is a magnetic field. And that protects us from some very harmful rays that come from the sun that are part of what we call the solar wind. And so we must never underestimate this idea of a magnetic field. What we recognize is that there's a follow-up idea of magnetic field, and that's magnetic flux. Magnetic field strength is represented by the letter B. This is the strength of the magnetic field. Now, flux, we're going to see, is the relationship, it has a letter phi, and it's the relationship between the magnetic field strength and a perpendicular area through which those field lines pass. And so phi, the magnetic field, the magnetic flux, is made up of two components, the magnetic field strength and the area through which these field lines pass. And we're going to use this quite extensively as we look at different aspects of electromagnetism. Now, here's a beautiful picture of a magnetic field. This magnetic material, which is probably iron filings, so little pieces of iron that have been placed on a piece of paper, and the paper's being tapped, and underneath it is a magnet. Now, at this stage, we don't know what's happening at this end or what's happening at that end in terms of the direction of the magnetic field. What we see is that at those two ends, there's a strong magnetic field because more iron filings have been attracted. Look, they're close together. They're not spread apart. Over here, they're quite spread apart. So when they're close together, it's a strong magnetic field. And in fact, because it's pointing in the same direction, the field lines will point in the same direction, we call it a pole. And so when we're dealing with magnets and we're dealing with the magnetic field, we have two opposite poles. We could have chosen any letters, but we've decided to call them the North Pole and the South Pole. So we have two poles, north and south, and they are different from each other, just in terms of the force that will be exerted on a magnet that's outside of the north pole of another magnet. And so this brings us to the idea of what's the direction of a magnetic field. Well, we can test it, and the way we test it is simply by using a compass. The direction of force exerted on a free-moving north pole. Now, a free-moving north pole is a fancy name for a compass. So a compass is just a little base with a needle on it, and on top of the needle there's a pointy bit, and on that pointy bit we have a piece of magnetized iron, and it has a needle on it. As I said, it's a little attached to that pointy bit there, and that end is north and that end is south. So if I bring a magnet over here and I make that north, then this north pole will be repelled, this south pole will be attracted. Opposite poles attract in terms of the magnets. And so we can determine the magnetic field by placing this little compass inside a magnetic field to give us the direction. If the compass points away, we're saying it's the field lines are away from the North Pole. If they're moving towards the end of a magnet, a bar magnet, then we'll say that is a South Pole. It's being attracted. The north end of the compass is being attracted by the South Pole of the permanent bar magnet. So just have a look. The direction of force exerted on a magnet when placed in a magnetic field. That's the direction. So the direction of the field is always the force on a compass. The direction of the force is indicated by the direction of the North Pole of the compass. Here we have another situation. It's also an example of a magnetic field. Let's have a look and see exactly what's happening here. We have a battery and a conducting wire. Recognize that there's a current that is passing from the battery, and it's passing through this conducting wire in that circuit. And on this piece of paper here, we've sprinkled some iron filings. Those iron filings have formed a magnetic field pattern. The magnetic field doesn't look anything similar to the one that we saw around the bar magnet, but it's still a magnetic field pattern. The magnetic properties of the iron filings have put themselves into a circular shape. So you can see it's forming circles around this iron on this piece of paper, around the conducting wire that's coming out. So the conducting wire is vertical, and at 90 degrees to that, there is the circular magnetic field that's taking place. It's not like the magnetic field of the magnet. So remember, at the magnet, when we had the bar magnet, and if we had to say this is the North Pole and that's the South Pole, we would get a butterfly type pattern where the field lines, we would write them in as coming out of the north, coming away from the north, being repelled at the North Pole, and being attracted at the South Pole. This is nothing like that. It's a totally different shape. But we can tell the direction in exactly the same way. So what are we going to use? That's right. We're going to put into this magnetic field, onto this piece of paper, where we see the iron filings have formed the circular shape, we're going to put little compass needles, small little plotting compasses. And here we have one, and what you can see about that one, it's telling us the direction of the current. It's saying the red end is the direction in which the magnetic field would be going. And so as we move it around, it would make this circular pattern. The point is that the compass shows us the direction of the magnetic field. Now, it's very important that we are able to determine and able to predict in which direction a magnetic field will be associated with a current passing through a conductor. And so we have a number of rules to do that. And the first rule that we're going to look at is the right-hand rule. Now, please remember, don't get mixed up. It's not the left-hand rule, it's the right-hand rule. So if you're right-handed, you need to take the pen out of your hand and make sure that's the hand that you're using. I happen to be left-handed, so I know it's the other hand. And look at exactly what we're going to do. We're going to use the thumb and the fingers of the right hand to give us the direction of the magnetic field around a straight conductor. And the way we do it is we say that the thumb is the direction of the current. So if we've got this, pretend for a minute that this is a conducting wire, and the red end is the direction in which the current is passing through. So that's the positive end. It's going from positive to negative. It's going up. Let's say that would be negative then. We're saying the current is going up. The direction of my thumb points in the direction of the current, and the curl of my fingers tells me the direction of the magnetic field. So if the current is coming out, you can see it's going in a circular pattern like that, and I can do it in any direction, whether it's going up or down. The important thing that it's going in a circular direction. If I were to switch it around and I say the direction of the current is down, well, then you can see on this side the current is coming, the field lines are coming out, and on this side the field lines are coming in. Whereas if I turn it around, it will be exactly the opposite. Now, you don't want to have to draw three-dimensional shapes of this, so we have a special way of showing both the direction of the current and the direction of the magnetic field. And we're going to use a series of dots and crosses to do that. So let's have a look at this particular example. The orange circle there represents a piece of copper wire that we've cut in cross-section. And the dot is telling us that the current is coming out. So the direction of the current is out. Now, have a look here. The thumb tells us the direction. So if the current is coming out, the thumb must be pointing out of the board, over here like this. So in which direction will the curl of my fingers be going? Well, I know it's going to be a circular pattern, and I'm now going to indicate the direction on the circular pattern by using my fingers again. And so if the thumb is out, on this side, the current will be up, but over here, the current is across to the left, and over here, it's down. The current is still coming out, and it's in that circular pattern. So over here, you can see it's anti-clockwise. It's not going in the same direction of a clock. What is important is that this is not a uniform magnetic field. It's not the same everywhere. And so the further we go away from the current-carrying conductor, the weaker the field goes. And we can represent that by drawing a second circle that's further away. The direction of the field lines will be in the same direction though, but they're not close together. They're actually weaker. Similarly, if I had the direction of the current going in, I'm going to use my thumb. I'm going to point the thumb going in, and the field is in the curl of the direction of my fingers. I'll draw one field in that direction. The second one, a little bit further away from it. The field direction is the same. Going in for the cross means in. And we can see here the direction of the field is opposite. They are not concentric. They're not the same distance away, because as we move from this point, from here, the field gets weaker. As we move outwards, the field decreases in its strength. Now, let's just be very clear about this and look at it in another perspective. And if we had a long piece of current-carrying conductor, what we'd recognize is this one. The current direction is from positive to negative. And if we now use our thumb in direction of the current, we recognize the magnetic field would be coming out at the top. Look, my fingers are pointing out over here, whereas they're pointing in over here. Pointing out, I'm going to draw these as little dots. And over here, I'm going to draw them as crosses. Now, there's one last little thing that I want to mention, is that the strength of the field can vary, and we use the symbol B to show that, and we use the unit Tesla, T, to measure it. Very quickly, magnetic flux is related to the strength of the field and the area. So over here you've got lots of field lines passing through that area, the same area but fewer field lines, so this one would be weak. And the magnetic flux, as I mentioned earlier, is this combination of the field intensity and the area. But remember, these two are at 90 degrees, they're perpendicular to each other, and we've got to use that angle theta to correct if they're not at 90 degrees. So I think this gives us a good overall summary of the ideas of the electromagnetism. There's a little bit more that we need to do, but first let's take a break. We'll be back straight after this. Welcome back from your little ad break. I hope you've got those points all about electromagnetism clear in your mind. Take a note, keep some notes as we're going through this. We're wanting to move on now. We've been talking about how the effect of a current is to produce a magnetic field. And in particular, we focused on the straight conductor. Now we're going to talk a little bit about the loop and the coil. The coil is sometimes called a solenoid. So let's focus on that and make sure that we've got those ideas very clear in our minds. Now remember, up until this point, we've been using the right-hand rule to indicate the direction of the magnetic field. The thumb points in the direction of the current. The field is given by the many fingers. So field and fingers goes together over there. Because we've got one current, we've got many fingers. But when we deal with a coil, it's slightly different. And so we have the right-hand solenoid rule. And I want to just go over the difference here. The first thing about a solenoid is that you have many pieces of wire. So on your right hand, you don't have many thumbs, but you have many fingers. So we swap around and we say many fingers. The current is all going in the same direction on a coil, so we'll use our current direction for the fingers. So the fingers will give us the current direction, and the thumb will do something interesting. It will give us the direction of the North Pole. So just as we've said, we use the fingers of your right hand to give you the direction of the current, and remember the current here is conventional current. Conventional current means it's from the positive to the negative terminal of the battery. The thumb points in the direction of the North Pole, and the North Pole is like the North Pole of a bar magnet. What we need to recognize at a North Pole of the bar magnet is that the little compass needle would be repelled at the North Pole, and so the direction of the field lines would be out at the north and coming in at the south. Field lines, when we draw them, please make sure, not like my fat pen that I've got, they should be drawn quite neatly and they shouldn't overlap. You usually draw them in pencil. They mustn't cross each other. They must be spaced apart from each other. They never intersect or lie on top of each other, space between them, and they must start and finish on the surface of an object at 90 degrees. So at 90 degrees to the magnet, that's where they'd leave. Okay, so the right-hand solenoid rule, we're going to apply it in a couple of situations. So I've drawn a little picture, sketch of a solenoid. And what you can see here is that it's just pieces of wire, copper wire, wrapped around a piece of plastic or piece of cardboard. This is not a conductor. This is usually an insulator. And we've got this as the coil. Now, if we're going to use the right-hand solenoid rule to establish the direction of the North Pole, well, we'll need to be able to recognize the direction of current. So we haven't been given anything, but I'll just add it in over here. Let's pretend for the moment that that's the positive terminal and that's the negative. So what we recognize here is that the current is going to be moving from positive towards the negative. And so when you use your right-hand solenoid rule, it's going to go, the fingers, many pieces of wire, fingers are going to go up, and the North Pole will be over there, which means the South Pole will be over there. If I was now asked to draw the magnetic field, well, that wouldn't be too difficult. What I would need to do is I would need to be able to say, well, my magnetic field is going to run from the North Pole, because this is an electromagnet. It is just like the bar magnet, away from the North Pole towards the South Pole, and I put little arrows to show that, and I'm going to do it exactly the same on the other side, away from the North Pole, all the way around and in at the South Pole. Now, that's on the outside of the bar magnet. On the inside of the bar magnet, the field lines run from south to north. So on the inside, they run from south to north, and we complete them like loops like that. Now, please be aware that we don't always have a completed loop. Sometimes in the field line pattern, we could have just lines coming out like that. They're coming out of the North Pole, and they'd be coming in at the South Pole, and we'd be able to show them like that. So that's the field line, and that's using the right-hand rule. But now things might get a little bit tricky, because we can have different views of a solenoid. And so here's another view of the solenoid. Wonder if you can see what's happened here. That's right. I've cut the solenoid in half, and I'm now looking at it from the top, where the dots and crosses are representing the direction of the current. So again, I'm going to use my right-hand rule, and I'm going to say, if the current is coming out on that side, right hand, current is coming out on that side, and it's going in on that side, like that, then quite clearly, this is the North Pole, and that means that's the South Pole. And if I were to draw the magnetic field again around here, recognize it comes from the North Pole around to the South Pole. And so it will go out of the North Pole and in at the South Pole, and I put little arrows to show the direction. Remember, these lines tell me that the current is coming out at that point, and it's going in at that point. And that's how I was able to use my right-hand rule to show it. Now, here's a final picture of a solenoid, which I think is quite interesting, because here we've got magnetic fields, and we're actually looking at the end of the solenoid. So we're looking at one of the poles. And what we recognize is that tells us the magnetic field lines are going in. So this is going in. So when the fields are all going in, that means that this must be a South Pole. And so you'll see that here there's high magnetic flux. The field lines are close together, where here the magnetic flux is weaker. What we also recognize is the direction of the current is given by the right-hand rule. So we can say going in on that side, coming out on that side. So the direction of the current is up over there. So that must be positive. It's going around, and eventually it will come out on this side. So if you have a look, coming out on that side, going in on that side. And so we've been able to tell the direction of the current as well. So the right-hand rule is very useful, both the right-hand rule and the right-hand solenoid rule. And guys, I think that more or less wraps up everything that you need to know about electromagnetism. Let's just make sure that we've got the summary sorted out. Remember, around every current-carrying conductor, there's a magnetic field. The magnetic field is perpendicular to the direction of the current. We use the right-hand rules to do that, and we use dots and crosses to represent the direction of either the current or the field. Welcome back, everybody. We're busy revising some concepts about electromagnetism. Let's go and have a look what we're doing. So we recognize, to start with, that there are two types of processes that take place when we're dealing with electromagnetism. We can have electric current that produces a magnetic field, and we can deal with that in terms of electromagnets, where we recognize current passing through a straight conductor or a loop or a coil will produce some sort of magnetism. However, there's a second option, and it's my favorite one, which says let's rather start talking about doing something to a magnetic field, and let's see if we can do something to the magnetic field and a coil, if we can make some sort of electric current. And so this is called electromagnetic induction. And that's what we're going to focus on right now. So just to remind you that with electromagnetism, we said a moving charge creates magnetic flux. But when we're dealing with electromagnetism, a change in magnetic flux produces an induced EMF, or potential difference. Now, if that potential difference is across a coil that's part of a closed circuit, well, then we will have an induced current as well. So take note that if we've got a closed a circuit, then we'll have an induced current. These are related to each other, and they're related simply by Ohm's law, where we know that R is equal to V over I. So you can work out, for example, the resistance of the coil. If you know the induced current was a certain amount, and you know what the induced EMF was, you can work out the resistance of the coil, just linking it to another section. But we're not going to focus on that. Let's rather focus on the process of electromagnetic induction. And so I remind you that it's all about a moving magnet and its relationship to a coil. So if we move the magnet towards this coil, then we're going to see that there's a change in the magnetic flux that is passing through the coil. The coil has an area that is perpendicular to the direction in which the current is moving, and you can see that if the current is moving up, there's an area in the middle of the coil that is kind of at 90 degrees to that. And so we recognize that the magnetic field lines are also going to cut through this area that's in the middle of the coil. And so we've got to recognize that there's a change in magnetic flux. When the magnet is far away from the coil, there are not many field lines. As it comes closer, there will be more field lines. And so we can determine what's going to affect the induced current. There are a number of factors to look at. And so the first thing that we're going to say is, what are these factors? Well, the first factor we're going to look at is the number of turns in the coil. Whether it's got one loop or two loops or three loops or four loops, all those loops together create a bigger magnetic field when there's current passing through it, which opposes the moving magnet, and that's important. So the number of turns on the coil is very important. The second thing that's important is the strength of the magnetic field. Now, you can get different magnets of different strengths. Remember, we indicate the strength of a field by the closeness of the field lines. And you can measure them. We measure the magnetic field strength in Tesla. And so we're able to measure and rate different magnets, bar magnets, solenoids. We're able to rate them in terms of, this is a strong field, strong magnetic field, this is a weak magnetic field, depending on different materials used. We also are able to look at the change in the magnetic flux. And the change in magnetic flux is generally created by the movement, by the motion of the magnet. So if the magnet is stopped, there's no change in magnetic field. There's no change in magnetic flux. And so there would be no induced current. In fact, if the magnet was moving at constant speed, then it would still not induce a current, not induce an EMF. But if it's speeding up or slowing down or changing direction, well, then it's going to have a change in magnetic flux. And so when we move the magnet into the coil and out of the coil, that's when we get a change in magnetic flux. Those factors are really important. And these were discovered and summarized by a very famous physicist called Faraday. Faraday's law is probably one of the most important laws that comes out of the 1800s. And it has had a huge impact on devices that we use in our everyday life. In fact, without the idea of Faraday's law, there'd be a whole lot of technology that we wouldn't have access today. So let's have a look at what Faraday's law says. Faraday's law says the EMF induced in a coil is directly proportional to the rate of change of magnetic flux. And here we have the equation. So I'm going to break it apart just for the moment. And I'm going to say, it's telling me that the induced EMF is directly proportional to the change in magnetic flux. The phi bit that represents the field strength times the area that is perpendicular, and that cos theta does the little correction if it's not at a normal area. But it doesn't just say it's directly proportional to the rate. It doesn't say it's proportional to the change in magnetic flux. It says the rate of change. And whenever we have the word rate, we need to include divide by time. And so that's why we've got this divide by time. I also want to draw your attention to the fact that there's an N out there, and that N stands for the number of turns on the coil. And so very clearly, what we need to recognize is that the induced EMF is also directly proportional to the number of turns. And that summarizes for us those factors that are going to affect the strength and the magnitude of the induced current, the induced potential difference. But let's just see if we can make sense of one further thing. And I want to interpret it in terms of that negative sign over there. The man that did the interpretation for us was a man called Lenz. And so we talk about Lenz's law. And in a more detailed way, he says that the EMF induced in a coil opposes the change in magnetic flux. And it does that by exerting a force on the magnet that is moving towards the coil. It opposes that change in magnetic flux. Remember, without the change in magnetic flux, there'd be no induced EMF. And so it might sound a little bit complicated. Let's simplify it a little. And so what we recognize here is that if I have a coil, and I'm just going to use this red line, red pen to indicate the magnet, and I'm going to use a blue line to indicate the coil, and I'm going to connect it to a galvanometer. At the moment, it's reading 0. And I'm going to say to you, I'm going to use a force to push the magnet towards the north, towards this coil. And so what Lenz's law says is if you push a north pole towards the coil, it will try and repel that motion. It will try and exert a force to prevent there being a change of magnetic flux. Remember, when it's far away, the magnetic flux is low. As it comes closer, the magnetic flux is getting bigger because there are field lines passing through the middle of the coil. And we want that to be reduced. So it's going to repel it. And so as the the north pole moves towards the coil, what happens to the pole at the end of the coil? Well, it's going to develop a north pole because north repels north. So it wants to create repulsion. Okay? It repels the magnet. And in that process, by creating a north pole, there is an induced EMF, there's an induced current that passes through the coil. Let's do one more situation, and let's make sure that we've got that very clear. So if I'm moving this north pole towards here, this end is going to become a north pole. Recognize that if the north pole moves away from the coil, so if I go back to that previous diagram over there and I say, let me just erase the writing there, and I'm going to say I'm moving the north pole away now. In which direction is the pole going to be at this end? Well, it's going to be a south pole because it wants to pull it back. So whatever the pole coming towards it, it wants to repel. If there's one that's moving away, it wants to pull it back. And so we recognize over here that if there's a north pole moving away from the coil, the coil develops a south pole. It wants to attract the magnet. And so that really summarizes for us the principal points of electromagnetic induction. I hope you've got those main points together. Take a short break and we'll see you directly after that. Welcome back. We're going to get into answering some questions that you might find in a test or a textbook, or you might even find them in an exam. It's important that we learn to apply all the main points on both electromagnetism and electromagnetic induction. So let's go and have a look at some examples that we've got here. So here, first of all, in this question, we've got the diagram shows a coil that's connected to a power supply. And the power supply is indicated by that positive terminal and that negative terminal. We recognize that the wire is wrapped around an insulator, and now we're going to see exactly what the questions are. So it says, indicate the direction of current through the coil. Now, that is really not difficult, but it's an important point to make, that whenever we are asked for the direction of current, we are dealing with conventional current. It's the direction a positive charge would move in a circuit or in a field. And so in this case, we recognize a positive charge would move from the positive terminal of a battery or power supply to the negative. And so we can simply recognize here that the direction of current is from positive. It's going to go up behind that coil, and it's going to come down on this side, and it's going to come down on this side, and it's going to come down on this side and come out at the negative. So there's the direction of current. Very easy to be able to work it, but you must make sure that you remember what conventional current is. Next question. It says, determine the north pole of the coil. So let me just quickly put those arrows in again and recognize that the current is in that direction, and we have to use one of the two laws or two rules to find the direction of the north pole. Now, in a solenoid, a coil, it's easiest to use the right-hand solenoid rule. Remember, we're asking for the pole. So there's one pole. So we're going to use the thumb for the pole, and we're going to use the many fingers to show the direction of the current. And so on this side, we recognize that the current is going up over there. It's going up at the back, and it's coming round on this side, over the front, and you can see my fingers are curled down over here, pointing downwards, just like those red arrows would be, and that tells me very clearly that the North Pole will be over here, and the South Pole will be over here. So that wasn't too difficult. Just need to remember to use the right-hand solenoid rule. Now, if by any chance you forget the right-hand solenoid rule, well, then it's really not too difficult either. We just need to remember the right-hand rule. Let me show you what I mean. And what I would do is I'd recognize the right-hand rule shows me the direction of the current. It tells me the current is going up. The field lines are going into the board at that point. So if I were to mark these field lines, I'd say they're going in at that point, around here. And that means that on this side, where the wire is coming down, the field lines are coming out. So if you look, there it's going down, one piece of wire, the field lines are coming out. So if I were to look at that end of that coil, what I'm recognizing here, I'm just looking at the other view, and I recognize that the lines were, the wire was going up over there, the direction of the current was going up, and I've already said when it's going up over there like that, the field lines, the magnetic field lines, are going into the board on this side, and they'd be coming out on this side. Now, as I move this red line around a little, and I'm going to just make sure I've got the red line moving around, and it's like that. On this side, it's moving down. And what I recognize here, using my right-hand rule, then you'd see that the field lines are going, the current is going down, the field lines are going in on that side. So outside of this piece of wire, I've got little crosses. They're going in on that side. What would they be doing on the inside of the coil? Well, that's not too difficult. They'd be coming out on the inside of the coil. So that means there'd have to be dots on the inside of the coil. And if I'm looking at that end of the bar magnet, of the coil, it's like a bar magnet. And where do we see field lines coming out? We see field lines coming out at the North Pole. So you can double check yourself. Just use the right-hand rule. But of course you need to practice it to make sure that you've got that right. So let's go to the next question. The next question says, draw a diagram to show the magnetic field around the coil. So I'm going to just simply redraw the coil for a minute so that I've got all the details right. I recognize that end is the north end, that end is the south end. I'm going to just put the pieces of wire on and say in which direction the current was going. So we've got that clear as well, and we recognize the current was going down like that. And at the back here, the current was coming up, and at this end, the current was looping over, and if I'm not mistaken, there was one that was coming straight down like that. So where this is positive, this is negative. Now, let's see what the magnetic field, because that's what we're asking. We're wanting the magnetic field around the coil. Now, the magnetic field lies in 3 dimensions, but it's much easier if we just draw it as a flat plane, okay? Because it's in the same plane as the wires as well as the coil. So we're going to draw that, and I'm going to just choose a slightly different color here and make sure that we've got those field line patterns being out at the North Pole and in at the South. So they're going to come in at the south and they're coming out at the North Pole. Right, I think we've covered that question, which was quite an interesting question, and it's important that we recognize this phenomenon of electromagnetism. Let's have a look at the next question. So here is a situation which says we've got a diagram below that shows a coil and a magnet with a pole P. So there's the magnet and it has a pole P. A magnetic field is induced in the coil due to the motion of the magnet. So the magnet is moving relative to the coil and we're needing to find out some things about it. Let's have a look. The first thing it tells us, determine the pole and direction of P if X is a north pole. So if X is a north pole, then what are the ways that P must be moving for it to be, for X to be a north pole? Well, quite simply, we recognize, first thing, if P was moving towards the coil, then it would clearly be a north pole. Because according to Lenz's law, we recognize they would repel each other. So as the magnet moves in, it would be repelling each other. Now, there is an alternative. We would also recognize that that might not be the only thing that could happen. We'd recognize that if P was moving in the opposite direction, in other words, P was moving away, then what would make that a north pole? Well, if it was a north pole, then they'd be repelling. No, that wouldn't be the case. This would have to be a south pole, because the whole principle is to undo or to prevent the change of magnetic flux. So a retreating south pole would be drawn back. It wouldn't allow it to create as much change in magnetic flux. Next question. Now, what's the direction of the current through the coil? Let's make sure that we understand. North is in that direction. Let's make this one north and let's make it moving in. Now, if that's the north pole, then I'm going to need to use the right-hand solenoid rule to be able to show the north pole at that position. And from that, I'll be able to tell the direction of the current. So if I know north pole is there, I'm going to use the curl of my fingers to say north pole is there, then the current has to be coming down on this side. It's going to be going up on the dotted lines, and in that way, I will recognize that this piece of wire is connected to the positive end, and this piece of wire that comes out here is connected to the negative end, and we recognize we've got the direction of the current. That brings us to have another look at our concept map of this whole topic of electromagnetism. Remember the important bits, that there are two processes. Electric current produces magnetic field. A change in magnetic field when it's linked to a coil will create an electric current if it's a closed loop. So please remember those two aspects. Practice the rules, the right-hand rule, remember the laws, Faradays Law, and do lots of practice. I hope this has helped you. From me, we'll see you again soon. Bye.